Hi grade 12s. We are looking at the vector equation of lines today. This is 11.9, it's page 25 in your booklets. So we've been studying about vectors. We're going to extend this into how we can express a line in vector form. We'll talk a little bit about the similarities with the way of expressing a line as y equals mx plus b or y equals mx plus c that you're already familiar with. So you can see in the diagram that we've got an origin. We have 4 points A, B, C and D that are all on a straight line. I'm sure you could find the linear equation that represents that line very easily. So today we're going to talk about how to find the vector equation. And basically the vector, we're going to think about the position vector of a point on the line. And it can be found if we know the direction the line is going in. I've drawn uphill. I guess you could also draw downhill as well, as long as it's parallel to that line. And we need to know a point on the line. And unlike when we express a line in slope-intercept form, it doesn't have to be the y-intercept. So in this diagram, we're going to start off by using the point A. You can see it has coordinates 1, 3, and the position vector of that, of course, is the vector 1, 3. Along 1, up 3 from the origin gets us to A. And the line is travelling parallel to the vector 2, 1. If I go from point A to B, I'm moving right 2 in the positive x direction. I'm moving 1 in the positive y direction. So that means I've travelled along this vector 2, 1. Okay, so the position vector of any point on the line can be given in this form. We need our point on the line, which was point A. So I've got 1, 3 here. And then I need the vector that's parallel to the line, which is the 2, 1. And if I multiply that 2, 1 vector, the vector parallel to the line, by some value, it will get me to another point on the line. For example, if I multiply, if I say that let t equal the value 2, I would have 2 lots of 2, 1. So let's quickly work out what that is. I'm going to do the scalar multiplication first. Oops. 1, 3 plus 4, 2. And that makes the point 5, 5. And if we check, yep, there's 5, 5. It's point C. So t equals 2 gets us to point C. Of course, we could use a negative value for t. I could use the value -1. Let's take the slightly lazy approach and keep part of this. So I'm going to do plus -1. So it will be, let's stick with plus then. -2 minus -1, which will give me a position -1 and 2. And if we check, that is point D. So that was t as -1. And of course, if I use t as 0, then that whole part is going to vanish and I'll just be left with 1, 3. So that would be A. I don't have to stick with whole number values for t. I could use any real number I like, really. So positive, negative, fractional, whole number. It will get all the points on that line. And I'm sure you will be able to work out that the t value for b is t equals 1. So there are some similarities with our y equals mx plus b form of a line. You can see that t is our input here, which we usually think of as the x value. You can see that we've got this direction vector, called the direction vector because it tells us the direction of the line, of course, and that links to the slope. So the direction vector tells us that we go along 2 and up 1. Well, the slope we normally think of as the rise over the run. So the slope would be a half. I'm taking the values from the direction vector. The y becomes the top, the rise, the x value becomes the run, which is the denominator of my slope. The plus b we usually think of as, it is the y-intercept. If we were working with the point slope form of the line, then maybe it would fit in even better with this. Because then y1 and x1, y1 is just our position vector on our line. Of course, we could choose any starting position vector. So it didn't have to be point A. It could have been another point. It could have been B, C, D. It could have been the y-intercept if we wanted, albeit we'd have had 0 and 2.5. It's probably easier with whole numbers, but it could have been any point. And equally, the direction vector we chose is 2, 1. I could have said the direction vector was 4, 2. I could have said the direction vector was -2, -1. So there will be multiple correct answers. Of course, all the direction vectors will be scalar multiples of each other. But the position vector, which is this first vector, is any value is up for grabs. Any value as long as it's on the line. Okay, so here's a little summary. The equation of the line is normally written as r equals a plus tb, where r is our positions on our line. We can use this in 2 dimensions or 3. Okay, so if we have a line that passes through point A and it's in the direction of the vector 1, 8, -2, I encourage you to pause the video, quickly write down how you would express that. Okay, hopefully you've written down the position vector, not with the parameter t, and the direction vector being multiplied by that value t. And of course we could put those together and we could say, well, the x component is the x component of the position vector plus t times the x component of the direction vector. And same with the y, 2 and 8t, and the z would be 1 minus 2t. So now this looks a bit different to our kind of y equals mx plus b that we're more used to. And it actually leads into another way of showing the equation of a line, which is called parametric form. So the parametric form means you're expressing the coordinates, the positions, in terms of another parameter, which in this case is t. So you can see all I'm doing is splitting up that vector and writing it in parametric form. Or indeed, I could write it as a set of coordinates, just the x followed by the y followed by the z. So the x is given by this, the y coordinate is given by that, and then the z is 1 minus 2t. And let's put that in parentheses. So 3 ways, well, actually there's 4 ways there, it's all slightly different ways of writing the different positions on that line. We've got this position vector, direction vector version of the vector equation of the line. We've got them combined, we've got the parametric equation, and then we've got the general set of coordinates. We're going to have a go at example 1. If you'd like to try it on your own, please pause the video, have a go at it, and you can check your answer. If you'd like to work along, then of course we'll do that now. Find the equation of the line L, which passes through the points A and B. So if we want the equation of the line, you'll remember we need a direction vector and a position vector. So let's start with the direction vector. The direction vector can either be A to B or B to A. It doesn't matter which one we use. I'm going to use A to B, it's alphabetical, no other reason than that. So I'm going to go 1, 3, -3. We've looked at finding that vector already. So this is our direction vector. If you went B to A, of course, you're going to have the negative version of this. And that is fine. Your t-values will be the negative version of my t-values. The other thing we need is a position vector. And for that, you could use point A or point B, because both of them are on the line. Okay, so for line L, I'm going to say R equals, I'm going to use point A, 1, 0, 2, plus T, 1, 3, -3. Okay, so this is my position vector. But it's fine if you used B as the position vector, it's fine if you used BA as the direction vector. All right, we need to state whether the point 3, 6, negative 4 is on this line. Well, what could we do? I guess if 3, 6, negative 4 is on this line, then 3, 6, negative 4 must be equal to this, because this equation is giving me the positions on the line. So for some value of t, it should equal 3, 6, negative 4. So let's look, let's check the x coordinate. So if I just take the x line, that's the 3 equals 1 plus t. Oh, that's pretty easy. T must be 2. Okay, so there is a value, of course there's a value, that gives us 3 for the x component. Let's see if t equals 2 also gives us 6 and negative 4. So when t equals 2, r equals 1, 0, 2, plus 2 times 1, 3, negative 3. Let's see, we get 1 plus 2 lots of 1, 0 plus 2 lots of 3, and 2 minus, or plus 2 lots of negative 3. So that's 2 minus 6. That is negative 4. Okay, so we can conclude that 3, 6, negative 4 is on the line L when t equals 2. If it hadn't have worked out, if it hadn't been on the line, we would have found our t value from thinking about x, just as we did, and then when we substituted it into our equation of our line, we just wouldn't have got 3, 6, negative 4 as our position vector. At least one of the y or z values would be wrong, and that would indicate to us that it isn't on the line. The line doesn't pass through 3, 6, negative 4. Okay, last step that we're going to look at today is to find the angle between the line L and this new line. So if we're trying to find the angle between the lines, we know that we can use the scalar product for that. We could also use the vector product, but that's a lot more work. So let's stick with the scalar product. But the trouble is, if I think about line L, which we found up here, and this new line I've got 4 vectors going on. That's too many vectors to be trying to do a scalar product with. So we need to think about which ones are going to be important for the angle. So I've got some sort of situation where, I don't know, maybe my lines are doing this. And we've got line L, and I'm just going to call this R for now. The bit that's going to give us the angle, it doesn't really matter about the position. Line L could actually go here. Sorry, that's a bit wonky, but you get the idea. It's still going to have the same angle. So it's not really the position, it's the direction that's important. So for this, let's get rid of that. We're going to use the direction vectors. Okay, so how are we going to find our angle? We're going to look at our formula guide, and we're going to say it is v dot w over the magnitude of v times the magnitude of w. And I'm going to use my direction vector from line L as v. I'm going to use my direction vector from this new line as w. Okay, and then I'm busy calculating and I'm finding theta. I will put up the answers on OneNote for that, so you don't need to watch me going through all the steps on the calculator for that. So yeah, we're using the direction vectors because that's the bit that's important. In reality, these are 2 lines in 3 dimensions. While we're finding the angle between them, there is no guarantee that they will be crossing. If you've got lines in 2 dimensions, as long as they're non-parallel, they will cross. In 3 dimensions, they could be the same line. They could intersect at some point. Or they could be what are called skew lines, which means they are two lines that don't meet but are not parallel. We can still find the angle that they make. We kind of think of like them being one being projected onto the other, and we think about what angle that projection would make. But yeah, it's just one thing to bear in mind is that these lines might not actually intersect, but we can still talk about an angle that's formed between them. All right, you can see that there are 3 different levels of homework. I would do your best to work pretty hard this lesson. I'm sure you've all got extended essay work to get going on this evening, so try and do as much as you can in class today. And hopefully I'll see you tomorrow and we can continue our adventure with vectors. Bye-bye.